Here we are at the very important topic of ligands. In this topic, we'll discuss why ligands are very important while studying the coordination compound chemistry. This is the roadmap of what all topics we'll be going through while studying the coordination compounds. And let me introduce myself. I am Harshal. To start with the ligands, let's start with the first point of the definition, as it's mentioned that the neutral molecule, cation or anion, which are directly linked to the central metal atom, are called ligands. Like you can look in the complex mentioned above that NH3 ammonia molecule is a ligand which is directly linked to the central metal atom or ion cobalt. Coming on to the second point, ligands always donate an electron pair and forms a coordinate bond. That is, the ammonia molecule will donate its lone pair to the cobalt atom and it will form a coordinate bond. So, as the ligands donate an electron pair, therefore they act as Lewis base. I hope you all are familiar with Lewis acid base concept. The below mentioned are the examples of the ligands. So a big concept to remember here is that ligands will always donate a pair of electron to form a coordinate bond. That is, they never donate single electron. You can see it is clearly mentioned below that the ammonia molecule and the nitrogen atom here has a lone pair of electron and it donates its lone pair of electron to boron atom to form a coordinate bond. So the bond formed here between nitrogen and boron atom is a coordinate bond. Therefore, it has donated its lone pair of electron. It will never donate a single electron. Now coming on to the types of ligands, on the basis of number of donor atoms, the ligands are classified as, the first category is mono or unidentate ligands. As the word itself clears, mono or uni is mentioned for a, it comes into single category. So ligands having one donor atom and donates only one electron pair to the central metal atom are mono or unidentate ligands. Come on to the second point, though there can be more than one lone pair, but only one electron pair can be donated per atom. So always remember in mind that a mono or a unidentate ligand will donate only one electron pair. It can have more than one lone pair of electron, but it will always donate one electron pair as it is a monodentate ligand. So below are the examples mentioned. I'll probably show you the structures of the monodentate ligands. Like, as we can see in the first structure of ammonia, that nitrogen has one pair of electrons. It is having one donor atom. Therefore, it is a monodentate ligand. Similarly, in phosphine, the phosphorus is the donor atom, so it is also again a monodentate ligand. In pyridine, look at the structure, it's so complex. When nitrogen is having its lone pair of electron and nitrogen has the capability to donate its lone pair of electron, therefore nitrogen will donate the electron and therefore pyridine is also a monodentate ligand. Coming on to the next structure of water, as oxygen is having two lone pair of electron, but we have learned in the definition that a monodentate ligand will have one donor atom and one donor atom at a time will donate only one electron pair. Therefore, oxygen atom will donate only one pair of electron. In the next structure of carbon monoxide, we can see that the bond, the triple bond formed here is itself a coordinate bond. As you all know that oxygen has 6 electrons in total and two of the electrons are busy in the formation of bond with the carbon, and the four electron are free electrons. So the above two electron which were present here, the oxygen donated its two free electron to the carbon atom, and it has formed a covalent bond here. So the two free electron present the carbon will donate these electron pair to form a coordinate bond, and therefore carbon is the donor atom. The electron donating capacity of oxygen is quite less here. Coming on to the next structure of azide, the any of the two terminal nitrogen atoms, any one of them can donate its electron pair. Coming on to the second category, that is polydentate ligands. So the ligands having more than one donor atom per molecule or a compound are called as polydentate ligands. The first category of polydentate ligands is bidentate ligands. That is, bi again mentions for a two donor atoms. So the compounds of the molecules having two donor atoms per molecule are called as bidentate ligands. The example is ethylene diamine. It is mentioned as En. You can see you can look at the structure mentioned below. The two nitrogen atom circled by red are the donor atoms here, and the M mentioned below is a central metal atom or ion. So the two nitrogen atoms will donate their electron pair to the central metal atom M. And ethylene diamine is also a type of chelating ligand. Now I'll discuss this chelating ligand further, as it is a very important point. The structure of some bidentate ligands. Look at the first structure of oxalate. The two oxygen atoms having three lone pairs each will donate one electron pair from each atom to the central metal atom. So you can look here, these two oxygen atoms which are having a negative charge over them, and they are having three lone pairs. So these both oxygen atoms can donate electron pair each. So there are two donor atoms available. Therefore, it is a bidentate ligand. Again, I have said that oxalate is a symmetric and a chelating ligand. Now, symmetric and unsymmetric refers here to that a symmetric ligand will have similar donor atoms, and an unsymmetric ligand will have two different donor atoms. Now look at to the second structure of dimethyl glyoxime. It is mentioned as DMG. The one nitrogen atom and the other oxygen atom will donate their lone pair of electron to the central metal atom. That is, you can look clearly in the structure. This nitrogen atom will donate its lone pair, and this oxygen atom will also donate its lone pair of electron. Therefore, dimethyl glyoxime is a unsymmetrical. I hope you are clear with that. It is having two different donor atoms, and it is also a chelating ligand. So, dimethyl glyoxime is your bidentate, unsymmetrical, and a chelating ligand. Now we have come to the topic we were waiting for, that is chelating ligand. So always keep in mind that a polydentate ligand is called a chelating ligand if it forms a closed ring structure. That is, okay, look at the very simple structure this mentioned here on the right hand side. This is what ethylene diamine, we have seen that earlier. So the nitrogen atom here is a donor atom. Similarly, this nitrogen atom is also a donor atom. So it is a symmetrical bidentate ligand. Similarly, the other ligand also present here is also ethylene diamine. So as you can see that when ethylene diamine is donating its electron pair to the central metal atom copper, it is forming a closed ring structure. You can look at this. It has formed a closed ring structure. So whenever there is a ligand, whenever a ligand which donates its electron pair to the central metal atom and forms a closed ring structure is called a chelating ligand. Coming on to the points mentioned below, that chelating ligands form more stable complexes. That is, when there is a closed ring structure, the stability of the structure increases, but also keep in mind that ligands with larger group forms unstable rings due to steric hindrance. That is, look at the structure which is mentioned in the left, that a complex structure. I hope you might be familiar with this structure. This is the structure of hemoglobin. Hemoglobin is a iron complex. Okay, so this is the central metal atom, and you can look at the donor atoms, your ligands, they are bulky. So due to the presence of bulkier groups, there is a repulsion between the bulkier groups, which is called as steric hindrance, and this steric hindrance brings instability in the compound. Coming on to the next topic of tridentate ligands, I hope you are clear now. Mono or unidentate ligands will have one donor atom, bidentate will have two donor atoms, and similarly the tridentate ligands will have three donor atoms per molecule or compound. So the first example is ethylene triamine. I hope again you are clear. It as ethylene diamine was for two donor atoms. Similarly, the diethylene triamine is for three donor atoms. So the three nitrogen atoms having an extra lone pair of electron, they'll donate it to the central metal atom and will form coordinate bond. As you can see in the structure, the three nitrogen atoms mentioned in the blue are having their lone pair of electrons, and all these three will donate their lone pair of electron to the central metal atom and will form a coordinate bond. So this entire molecule or a compound itself is having three donor atoms, therefore it is a tridentate ligand. Look in the structure that is mentioned below. This is called as terpyridine and mentioned as terpi. So the three nitrogen atoms will donate their lone pair of electrons and will come into the category of tridentate ligands. Look at this, some important ligands. The first and the very important ligand is EDTA, that is ethylene diamine tetraacetic acid. Okay, I hope you are clear with the name, why it is named as EDTA, ethylene diamine. See, look, this is ethylene and diamine tetra. Tetra will mention four. The four acetic acid groups are present these ways. Okay, the above structure has six donor atoms. So as it is having six donor atom, it will come into the category of polydentate ligand and also known as a hexadentate ligand. The donor atoms in EDTA are four oxygen atoms with negative charge. I hope these are clearly mentioned here as 1, 2, 3, and 4, and the two nitrogen atoms here present at the ends. Okay, so always keep in mind the structure of EDTA. It is a hexadentate ligand and a very important structure. Similarly, look at the structure of glycinato. Glycinato is actually formed by the deprotonation of amino acid glycine, and the oxygen atom present here and the nitrogen atom present here will donate their lone pair of electron to the central metal atom. So it is a bidentate ligand as it is having two donor atoms, and I hope you are clear. We have earlierly studied that it is also a unsymmetrical ligand, okay, because it is having two different donor atoms. Now coming on to the third and the very important category of ambidentate ligands. Now this is something new. Let's learn this. The ligands which have one or more donor atoms, but during the formation of complex, only one atom can donate the electron pair. Look at the structure. This will make you very clear about this, that there are some structures or the compounds or the molecules, they are having more than one donor atoms, but only one of the two donor atoms can donate the electron pair. Okay, So I hope you are clear with the ambidentate ligands. Those ligands which can have more than one donor atom, but only one atom will donate its electron pair. See into the first example, look into the first example of nitrito N. Actually, the compound is NO2. So when in this compound, this oxygen atom is also having lone pair of electron, and this nitrogen atom is also having lone pair of electron. Both of the atoms are capable of donating the electrons, but as we have learned that only one of the two atoms can donate its electron pair. Therefore, if nitrogen donates the electron pair to the central metal atom, it will be written as nitrito N. And if oxygen donates the electron pair to the central metal atom M, then it will be mentioned as nitrito O. Okay. Look at the second example. Similarly, if sulfur donates the electron pair to the central metal atom, it will be named as thiocyanato. And if nitrogen donates the electron to the central metal atom M, it will be named as isothiocinato. Okay. Now coming over to the last topic, that is denticity. Denticity refers to the number of donor atoms or groups in a ligand that are directly linked to the central metal atom. Remember the number of donor groups or atoms in a ligand, that is monodentate. The denticity of monodentate ligands is 1, bidentate ligands 2, tridentate ligands 3, and so on. So example, in the examples, it has mentioned that EDTA, the denticity of EDTA is 6 because each EDTA molecule has 6 donor atoms. Okay. So the total number of donor atoms present in a group is the denticity of that ligand. Similarly, ethylene diamine will have 2 donor atoms, therefore its denticity is 2. And for ammonia and water molecule, the denticity will be 1. So I hope I have made you very clear about the theory of ligands. Now stay tuned for the next video. It will be uploaded soon, and keep practicing. Thank you.